Okay, next up we're going to take a look at what's called the edit distance problem. And the edit distance problem, in the edit distance problem, we have a source string and a target string. And what we're interested in knowing is what is the least number of editing operations that we have to perform on the source string in order to convert it or transform it into the target string. 3 editing operations are permitted. We can either insert a character into the source string at the current location, or we can delete a character from the source string at the current location, or we can replace one character in the source string with some other character. Generally, we're going to choose the character from the corresponding position in the target. All right? Now, as usual, we don't know in advance which particular ordering of which editing operations is going to produce the best result. So what we're going to do is to try all 3 of the possible solutions and then figure out when we're done which one was the best. Okay? The setup for this, without getting into the whole recursive setup and so on, it's going to end up being very similar to the longest common subsequence problem that we looked at previously. We're going to have an array of cells with the target string. I'm putting the target string at the top, and the source string so the target string is for the columns and the source string is for the rows. And then what we are going to do is to fill in the edit distances between increasingly long prefixes of these strings. Okay? We're also going to have a column and a row for empty strings. All right, so let's take a look at what we're going to do with this array. Now, in the first column represents deletion of characters from the source string in order to match the target. So if our target is the empty string and our source string is some prefix of the word banana, then if the prefix is itself the empty string, there are no editing operations we need to perform in order for that part of the source string to look like that part of the target. On the other hand, if the source string prefix has a B in it, then in order for that to be transformed into the empty string, we would have to delete the B, so that's one deletion operation. Similarly, if we have BA, we're going to have to delete 2 characters to transform that into the empty string, and so forth. So if we have as our prefix of the source string the entire string banana, we're going to end up having to do 6 delete operations to make that source string look like the empty string target. Okay, now the first column, that was filling in the number of editing operations for the first column. Now let's take a look at the first row. And the analysis here is basically the same. If we're comparing this empty string prefix of banana, the source, with successive prefixes of the target string anaconda, well, we've already filled in the fact that our source string is already equal to the empty string, so we don't have any editing operations to do there. And what we're showing in the row, as opposed to the columns, is how many insert operations we would have to do in order to convert the source to match the target. All right, so if our source prefix is an empty string, we don't have to do any editing to make that equal to the empty string. But if our source is the empty string, we're going to have to insert 1 character to make that equal to the prefix A, or 2 characters to make that equal to the prefix AN, or 3 characters for ANA, etc., out to, we're going to have to insert a total of 8 characters in order to convert this empty string into the target string ANACONDA. Okay? So we now have our first column, which tells us how many delete operations we would have to do to convert increasingly long prefixes of the target, increasingly long prefixes of the source into an empty string as the target. And we've got our first row, which tells us how many insert operations we would have to do on the empty string as a source in order to convert that empty string into successively longer prefixes of anaconda. So far, so good. Those are pretty straightforward. Now we want to answer the general question. Okay, so if we've got some particular cell in the in this matrix, our intention is that that should represent or tell us the minimum edit distance that it takes to get the source up to that row I to match the destination up to the column J. All right, so we're looking at minimum edit distances for successfully. Come on, tongue, you can do this, I know. Okay, so we're looking for minimum edit distances to convert increasingly long prefixes of the source into increasingly long prefixes of the target. Okie doke. So, what can we say about this cell in the next row, in the next column, below and to the right of some cell Dij? Well, we have the edit distance for some source and target prefix. And we will have also filled in the edit distances for or let's assume that we have filled in the minimum edit distances for one additional character in the source prefix and one additional character in the target prefix. Now, we can get away with that assumption because we have already filled in the entire first row and the entire first column. So if we look at this cell here, which is currently empty, the D sub 1 sub 1 cell, it does have values to its left and above it, and also diagonally above it to its left. All right, so if the two subsequent characters match, then there isn't actually any editing that we have to do. We're just going to extend both the target prefix and the source prefix by one more character, and we don't have to do any editing. We're just extending the two prefixes. And so we're just, in that case, going to copy down the edit distance to the upper left. Okay, so we're just going to do this diagonal copy downward. On the other hand, let's suppose that these two characters here are not the same. All right, so in order to in order to modify the source to match the target up to that next position, D sub I plus 1 comma J plus 1. Well, let's think about this. So each of these other cells here is the minimum edit distance required to get the source prefix to match the target prefix up to this particular row and column. All right, so M in this little diagram here tells me how many edit operations I would have to perform in order for the source to match the target with the source up to row I and the target up to column J. Now, we also know the edit distance in order to make the target one character, in order to make the target prefix one character longer. We have that edit distance. And we also know how to find the edit distance for the source and the target if the source is one character longer. All right, so let's say, just to try some numbers here, let's suppose that it takes let's suppose that the edit distance to get up to that point in the upper left corner of this partial piece of D, let's suppose it takes one operation to get there. And let's suppose that it takes two operations to get one more character in the target, and perhaps it also takes two more characters to get one more character in the source prefix. So this is a 1, and these things here are 2's, let's say. Well, we can get from this 1 on the diagonal to this next cell by doing a replacement operation. Okay, replace is one of our allowed operations. So if we can get to this portion of this little 2 by 2 subset of D, if we can get there in M edit operations, then we can get here with M plus 1 edit operations, because we get to here with M, and then we do a replacing A with B, and we get to here. On the other hand, if N is our lower number, we can just add one more editing operation to N. Or if P is our lower number, we can add one editing operation to P. Going from this cell containing N to the lower right cell is a deletion operation from the source, whereas going from this value P to the next cell in the target direction would be an insertion operation. Let me say that again. So going from N to the new cell would be an insertion. Would be a deletion. Let me back up. Okay, so deletions are indicated by moving downward in the array D. Insertions are indicated by going to the right in D, in the same row. Replacements are indicated by going diagonally from the upper left cell to the current cell that we're trying to calculate. Okay, so we have deletion, an insertion, and a replacement. And we want to find which one of those is the minimum. That is, if we do an insertion or a deletion or a replacement, which one of those will give us the minimum edit distance for this new cell that we're trying to fill in. Okay, so it's 1 plus the minimum of those 3 cells. So, using that little formula that we've puzzled out, we can now take a look at how to fill in the second row. Now, the second row, we're comparing a prefix of the source consisting just of the character B with increasingly long prefixes of the target anaconda. And you'll notice that to get our prefix B to match an empty string, we had to do a deletion. Okay, we had to delete the B. And now we're going to need to insert an A, N, A, C, O, N, D, A. So we've got 8 editing operations that we need to do to convert the source string B into the target string anaconda, as we have increasingly long prefixes. Then for the next row, notice that if we start with the prefix B, we had to do a deletion to cause B to be converted into an empty string. Now, once we've done that deletion, the next two characters that we're comparing in the extended prefix of the source and the next character in the prefix for the target, those characters are equal. And our rule was that we then just copy down the diagonal value. Let's think about whether this makes sense. Does it make sense that the source string prefix BA is only one editing operation from the target string prefix A? What do we have to do to convert BA into A? Well, indeed, we only have to do this one deletion operation, which is what we needed to do to cause B to match an empty string. If we need to do one deletion to cause B to match an empty string, then we also only have to do one operation to cause BA to match A. And cruising along here similarly, here's another A. So there's another case where we simply copied down the diagonal value. How can we convert BA into ANA? How can we do that in just 2 editing operations? Well, what we can do is to replace the B with an N and to insert an A in front. So we can convert BA to ANA by inserting an A and replacing a B. So we can get to that position in doing 2 editing operations on our source prefix of BA to cause that to match the target prefix ANA, and so forth. And we continue this same thing with the 4th row. Let me just randomly grab another one here. So here we have these 2 N's match. So the N in the 3rd slot in banana, the 3rd character in banana, is the same as the N in the 6th slot of anaconda. So there's no editing operation we need to do in order to extend those prefixes by that N. We come down from the diagonal, and what we would do is to replace the A with an O. Then we would insert the C, and the A matches between the two. We would replace the B with an N and insert the A. So we've inserted the A. That's one edit. We've replaced the B with an N. That's a second edit. We didn't need to do anything for the A. We inserted the C and then inserted the O. There's our 4th edit, and that gets us to having the 2 prefixes match. The edited source prefix with those 4 edits now matches anacon. Okay? Okay, so you can walk along applying our little formula here to fill in the 5th row and the 6th row and the 7th row. And now we finally have an answer to our question. The minimum edit distance in order to transform the source string of banana into the target string anaconda is 4 edits. Okay, the lower right value here, the lower right corner here, gives us that minimum number of edits that we have to do to transform banana into anaconda. Now, I did a little bit of sort of hand-wavy backtracking for a couple of examples, but let's convert our backtracking algorithm to make it a little more systematic so that we can just read out now from this array D what edits we have to do in order to convert banana to anaconda with the minimum number of edits. So let me come up here to slide 13. All right. So this 4, as I said, that's the minimum number of edits we need to do, supposedly, to convert the source banana into the target anaconda. And we only have 3 editing operations that are allowed. Well, I guess maybe we should add no editing as an alternative. If the 2 characters directly match, for example here, A is equal to A, so there's no cost in getting that final A. There's no editing required at that step. And you can see that we just come down from the diagonal. Once we've got banan edited so that it matches anaconda, then we just extend those 2 by 1 more character, and that gets us to the conclusion of the source string and the target string. Okay, so no editing is one possibility, but we also have, if we go to the left, working back toward the upper left corner, if we go to the left, that implies that we must have done an insert. If we go diagonally, that must imply that either we did no editing at all, or if the 2 characters do not match, that means that we did a replacement operation. And if we go up, that means that we did a delete. Okay? So what we want to do, starting from this lower right corner, is to go to the lowest cell to the left or up, or the diagonal up and left. And because going up and left, because going diagonally will get us closer faster to the beginnings of these 2 strings, if we have a choice between a couple of different alternatives with the same edit distance, we'll choose the diagonal. All right, so starting from this edit distance of 4, where we have these A's that match, we're going to go up to this diagonal 4. From there, we have 3 is the lowest of the 3 choices, so we're going to end up doing an insert operation. From there, we have a choice. We can go to one of these 2 3s, but we're going to prefer to go to the diagonal. All right, and that makes sense because these 2 ends are the same, so that must not involve doing an editing operation. So we didn't actually need to do an editing operation to get from the matching A's up to the N versus D. We had to insert a character to get to the matching N's, and there we don't have to do an editing operation. Then we go to the 2 here, and from there to the 1, and the 1, and the 1, and the 1, and the 0. Okay, so we did have a couple of choices early on. We could have gone to the left or diagonally in a couple of cases. But once we get over to this 1 here, we're sort of out of choices. We have to just follow the 1 up, and then we have one final upward motion, which is a deletion to get us to the upper left corner. And let's see what editing that implies. All right, well, because we want to do our editing in the order from the beginning of the prefixes down, instead of trying to go backwards, we'll start from the upper left corner where we just have banana versus anaconda. And the first operation that we need to do to convert banana to anaconda, since that's a downward step, that implies that we're going to delete the character B. All right, so that's our first edit. And that converts banana into unana. Now, notice from there that these two A's are the same, these two N's are the same, and these two A's are the same. So there are no editing operations necessary. Once we've done our first deletion of this B, there are no further editing operations necessary in order to make Anna match Anna, that is Banna with the B deleted. All right, so now we're down to this point. Why won't it let me highlight? Okay. All right, so now we're down to this point here. All right. Now we're going to the right. That implies that we're inserting characters. So ahead of the, so we've got everything matching up to A and A now. And the next thing we need to do is to insert a C. So that's our second editing operation. And the next thing we need to do is to insert our O, which is our third editing operation. Now, once we insert our O, the two N's match, so there's no editing involved in going from anacon to anacon. And the final edit that we have to do here is to insert another character, which is the D. So that's our fourth edit. And then there's no final edit because the A's match. And so you can see now that by deleting the B, inserting C, O, and D at appropriate places, we've done 4 editing operations in order to transform banana, our source, into anaconda, our target. Okie doke. So obviously, because we have a table of rows versus columns that we traverse through using a doubly nested loop to index the the row and column in this matrix, this is an order n squared algorithm. Sometimes this problem is presented with a slightly more complex formulation. It is possible to specify that each of these editing operations has a different cost. So our assumption when we set this up was that insert had a cost of 1, delete had a cost of 1, and replace had a cost of 1. That is, all 3 of these operations had an equal cost, and so our formula was quite simple. Once we had the first column filled in and the first row filled in, which are easy to do, we could then fill in the successive diagonally downward columns and rows using our little minimization formula here from slide 6. But now, if we have this alteration where, in this case, we're allowing insert and delete to have the same cost, but replace is going to be twice as expensive, you could conceivably have 3 totally different costs for each one of these 3. Now our formula is going to change. And so if it's twice as expensive to do a replacement, then if we don't have to do any editing at all, that's still free. So if we have the next 2 characters to extend the target sequence, the target prefix and the source prefix, if those characters are the same, then it's 0 cost to extend those 2 prefixes. But in the case where the two characters are different, now, in order to get from one of these other cells to fill in this cell for A versus B, we're going to have to figure out the minimum of 2 plus the replacement, or 2 plus M, okay? 2 plus M is the cost of doing a replacement, or 1 plus the cost of doing an insert, or 1 plus the cost of doing a deletion. All right, so our minimization computation alters. Well, now that we figured that out, we can still just mechanically fill out the table as we did before, and we can then backtrack from that lower right corner back to the upper left corner to figure out what sequence of editing operations minimizes the cost-weighted edit distance in this case. Okay, so that's that one.